Hi, and welcome to the Computer Architecture Podcast, a show that brings you closer to cutting edge work in computer architecture and the remarkable people behind it. We are your hosts. I'm Suvinay Subramanian.
And I'm Lisa Shu. Our guest on this episode was Vijay Janapa Reddi, an associate professor at Harvard University and vice president and co-founder of ML Commons. He has made substantial contributions to mobile and edge computing systems and played a key role in developing the MLPerf benchmarks. Vijay has authored the machine learning systems book MLSysBook.ai as part of his twin passions of education and outreach. His work has also earned him numerous accolades, including the IEEE TCCA Young Computer Architect Award in 2016, induction into the Micro and HPCA Halls of Fame, and multiple Best Paper awards.
On this episode, Vijay discusses Architecture 2.0, a new era of using AI and ML for computer systems design, exploring the opportunities, challenges, and educational shifts it necessitates. He also delves into his work on TinyML, enabling machine learning on resource constrained devices, and its potential to transform our technological interactions. A quick disclaimer that all views shared on this show are the opinions of individuals and do not reflect the views of the organizations they work for.
Vijay, welcome to the podcast. We're so excited to have you here.
Thank you for having me. It's a pleasure being here.
As longtime listeners of the podcast usually know, our first question is often, in broad strokes, what's getting you up in the morning these days?
It is without doubt my 4-year-old and my 8-year-old first thing in the morning at about 6 o'clock. And I'm sure that's very common for a lot of people.
6 is rough. I got to tell you that. 6 is rough. I got 7 a.m.ers, so I got lucky.
Well, we get some midnight wake-up calls, so.
Yeah, so after they get you up, then what is your day looking like these days?
Most of the time, it's kind of thinking about what's the next big thing that's actually happening in our field. That's honestly what kind of really keeps me up, thinking about it quite a bit. And I think because right now, it's such an exciting time when there's so much change going around, and finding the path through this nebulous cloud that we're looking into is sort of like the most fascinating thing, I feel, because it is both an opportunity for a whole bunch of different ideas that we can all explore in research and education. And at the same time, it's also quite a challenge because it's easy to kind of go down, a rat hole. So just thinking about that and trying to identify what are the interesting areas is sort of the most exciting thing right now.
Right. So one of the themes that you have talked about in recent times is what's called Architecture 2.0, a shift from the traditional paradigm of how we design computing systems. So what sparked this particular vision, and what are the most exciting advancements that are driving this particular paradigm shift?
Yeah, so that's a great question. So Architecture 2.0, just for the listeners to kind of be clear about, Architecture 2.0 is fundamentally just thinking about how we use AI ML to help us build better systems in the future as we're starting to build increasingly more complex systems, and to do that very efficiently, and to also do that with extreme sort of consciousness about like how we reduce time to market. Because I think as systems get more complex, validating, verifying, designing, all of that gets inherently more complicated, and so we need new tools. And that's fundamentally what Architecture 2.0 is really about. And obviously at this given point in time, it's a super exciting time because it's like we're in this era of not only just AI ML, we're truly in this era of generative AI ML, right? Which is sort of a very exciting area. Now, the reason that actually came to light is honestly just from reflecting all the work that's been happening in the community. The architecture community has been doing some very interesting work. Obviously, we build a lot of systems for ML, without doubt. But in recent years, we've definitely seen the shift towards having AI ML being used for machine learning systems, right? Like actually designing the systems in itself, right? So this could be in the form of like, whether it's Bayesian optimizations or genetic algorithms or reinforcement learning, or pick your favorite, bell whistle that you want to apply, right? And it's been like reading those papers that have actually been coming out, which I think in all honesty are fantastic and phenomenal because they're showing sort of, what's possible. But once you take a step back and you try to think about like, how do we systematically translate or convert this into something that we can use in a practical sort of sense, you start getting into some really deep questions about what are the challenges around this space. And from reading those papers is when I kind of realized, oh, wow, we don't really have an engineering principle around how we're going to be applying this methodology in order to accelerate all the traditional stuff that we've been doing. And I think that's fundamentally what gave birth to going around and talking to a large number of community members around what are the new challenges as we try to use AI ML for system/architecture design.
I think there are like several themes that you've talked about within this broad umbrella, from everything from data sets to ML algorithms to tools and infrastructure that you need. And as you rightly pointed out, new methodologies and a new way of thinking about designing these systems. Can you tell us a little more about these different themes? What are some of the challenges and opportunities that you see under each of these?
And I think the big and most fascinating element of all of this, as much as we talk about, whenever we talk about AML, by and large, most of the community is wickedly excited about, oh, I've got this new little model that I'm actually going to put in and it's going to do blah, blah, blah. Fundamentally, I think it's the most boring aspect of, AI ML, in all honesty. I think the most fascinating aspect of it is where it all begins, which is the inherent data that we're actually talking about, right? Because data is effectively the new code today. And when we kind of think about it from how do we apply AML methods for system design, and you kind of go back and you look at like, okay, what corpuses do we have? Question is very simple. What's the ImageNet data set for computer architects? That's a very simple question. And yet we would struggle to answer that question. Why? Because we have not systematically thought about it. We are the ones who have actually been building the systems that enable, all this AI technology, yet we ourselves have not thought about how we would be able to use it, in a very methodical sort of a manner. And so for me, the very first step is really about, can we build data sets for, architecture design? Now, architecture design is a very complex thing. It spans many layers, right? It goes all the way from talking about high-level design space exploration. In my head, it also cuts straight through the EDA flows, because at the end of the day, when we talk about architecture, it's not about just a design that we come up with. It's actually, how do we take it down to implementation, right? And so everything from that top all the way down is sort of like, the critical thing that I think is fascinating. And how do we think about data there is one of the first and foremost things we got to ask ourselves if we want to actually, use this new methodology in our existing workflows.
Well, I'm very curious to hear what you mean specifically by this kind of data exactly. Because, when I think about sort of maybe architecture 1.0 of how we would build things, the data would be, say, like some sim points or, spec basically. That's the data that we use to essentially not train the design, but sort of inform what we want the design to be good at. And that's the data that we test against, that's the data that we design against, and that's the sort of performance benchmark metric. In this case, it sounds like, obviously the data would be slightly different in this world because it's going into these AI ML techniques to try and inform these designs and do them rapidly and optimize them. So, obviously the word data is extremely broad. Maybe you can dive down a little bit into what you mean or what kind of different pillars of data you're talking about.
Yeah, pillars of data, that's a good way of kind of putting it. I think there's three fundamental ways of kind of bucketing these things, right? The absolute cutting edge one would be, how do we get data in a format that's actually useful for generation, right? Another pillar is, how do we get data in order to do sort of optimizations? And the more basic one, in all honesty, is like, how do we do some sort of prediction data? So in my head, there are these three pillars. You start with, getting data sets where we can make very basic predictions about what's going to happen next. The next thing would be, how can I get the data in order to actually design the system to be much more, optimal for some, whatever heuristic you choose to. And the third one really is the generative aspects. And I think once you kind of bucket things into these three major pillars, then you can systematically think about, what needs to be done. Now, off these three, obviously, prediction and optimization are things that we have been doing in the past, right? Because when we do design space exploration, we are effectively looking at, various design points and trying to, figure out what's the best optimized method that we have to kind of pick from. Even if you're looking at prediction, we've done prediction. We look at, prefetchers and branch predictors. They're all looking at, data coming through and making predictions, right? There is, however, a difference when we talk about prediction, optimization, and generation once we start thinking about it in the context of architecture 2.0. It's an incremental step. That incremental step in my head is fundamentally about breaking the abstraction layers, right? So traditionally what we have done when we have thought about optimizations is, by and large, we've been kind of focused on these abstraction layers from the system stack, going from the application algorithm all the way down to the hardware. We've created these multiple layers of abstraction, ISA being the most classic version of it, right? We create these nice abstractions between the hardware and the software ecosystems and kind of let each independently evolve. What ends up happening then is that you sort of do these smaller optimizations. And I think as you start getting into the AI space, what's really interesting is it's kind of stepping away from this traditional paradigm of instruction set architectures to more about parameter set architectures, PSAs, as I like to think about it. And the idea of PSA is that in the future, you still need to be a core architect. Don't make a mistake. I'm not saying that suddenly, our students don't need to know anything about architecture. All our people still need to know everything deep inside, so we know when models are hallucinating and so forth. So we take that fundamental understanding, flip that vertical stack into a more horizontal stack, and then our future architects are really going to be understanding what are the parameters that are actually essential to expose across each of those, horizontal layers. Because at that point, once you expose the parameter space, then you let the AI agents actually get to work. And at that point, it gets really fun, because now you could have an agent that's perhaps just dedicated to the hardware module, or you can obviously break it down into the individual microarchitecture components and have multiple agents all kind of working and learning from each other. But in the end, when you take a step back, they're effectively learning from each other and exploring that massive design space that we truly have across the system. And I think that sort of paradigm shift is really what we need to have, rather than thinking about things in a very traditional sort of a perspective about how we have done things today, right? I think that sort of changes, what architecture 1 to 2 is going to be.
That sounds very interesting. I think I want to double click on this idea of this horizontal design space that you were talking about. It sounds like, and let me make sure I heard it right, that, of course, we have this, a lot of layers, cross layer, and we often do cross layer optimizations, but they're usually in adjacent layers. Are you saying then that you turn that on the side, those layers from like ISA all the way up to, microarchitecture, turn that on its side so that an AI can look at all of the layers together and essentially optimize the parameters that we decide are good for exposure across what has traditionally been vertical stack, but now it's horizontal, and they have the purview of the whole white space. Okay, exactly. Interesting.
And I think that's going to be super fun, because you start to kind of understand that there are going to be differences about how we even expose those parameters, right? There might be hierarchical parameters. You want one AI agent to kind of, maybe just work on the memory subsystem in complete isolation. Or you might actually want to break the memory controller completely down and say, okay, even within the memory controller and the way it interacts with the memory subsystem might actually have multiple agents, because some of them might be responsible for very specific parameters that they're playing around with. And so when you kind of think about it, you get into this really interesting design space of how do you get the AI to actually map onto this horizontal parameter space that we're actually exploring. And those kinds of things have not yet been fully explored, because as you said, Lisa, we have largely been doing co-design between 2 adjacent layers. We lump it into hardware and software co-design, which is true. But if you really go into it, it's really just algorithm and hardware co-design in this very tight binding. But there is so much more to what an architecture, stack really is, right? And there might be optimizations that we would perform at the highest levels of the stack that are in fact suboptimal when you actually look at it from a holistic system design, because sometimes you want to leave more room for the system at the lower levels of the stack to actually make other kinds of, opposite decisions to what we would normally do.
Yeah, that's fascinating, because I feel like a lot of times, when you are a student doing microarchitecture design, even, maybe you've honed in on some substructure within the microarchitecture, whether that be a BTB or a TLB or an L2 cache or whatever. And you kind of do have to isolate yourself into looking at that structure in and of itself. You've got to get yourself a pattern stream that goes into it. And then within that pattern stream, you isolate yourself to figure out, okay, here's what happens here. Maybe I need, if I like memory systems, so like maybe you need an 8-way cache, or maybe you need a 4-way cache, or maybe you should have, and even with those dimensions of like how many indices, how many ways, how many megabytes, gigabytes, whatever, depending on what level of the cache you're talking about, that often was a relatively taxing space to look at just because, you would still have to run lots and lots of jobs. We didn't have the computational power. And you would wonder sometimes, like, okay, well, what if I change something in the L2 that changes the traffic? Like the way that the L1 is filtering to the L2, now the traffic has suddenly changed. Like there was no way to pop all the way up. And so it sounds like what you're saying is that if we turn everything on its side, and now that we have the massive power of all this AI, we can look at everything potentially all together, although we probably still have to be judicious about what parameters are being exposed. Is that what you mean by the first piece, the prediction piece and the data piece?
Yes. And I think it's the architect's job still to have very deep knowledge about what parameters are actually critical. So this by no means undermines, what a traditional architect is doing. If anything, all we're trying to do is, for instance, if we go back in time, and he says to kind of help you just compute through faster so you can actually look at more interactions with your fundamental knowledge.
I want to circle back to the data itself, and the quality of the data is very important for the quality of the AI systems or agents that we build towards these different tasks. This is true even in other domains. So if you look at the toolkit that we have to create such data, we have simulators on the one hand, and then we have real world performance profiles on the other hand. So how do you think we should go about collecting these data sets for architecture research? What should we be careful about, especially as we try to ground this data in the real world? Like we want to ensure that if you're simulating, the quality of the data should be good, which means that it needs to correlate in some reasonable manner to what we might expect in a real system. So how do we think about these different attributes of the data and the quality of the data? And what are mechanisms that we need so that we can create these data sets, curate these data sets, and then also measure the quality of the data sets themselves?
Yeah. I'm going to split the data element up into two fundamental pieces, which you were already alluding to. The first piece being quantity of data, because we do need, these are inherently having to be big data oriented kind of problems, right? And another one is once you have that big data, then sort of how do you tune it around for quality? Both are actually needed. If you kind of look at what's actually happening in the AI community, if you historically kind of look at the size of the data that's been evolving for images, for instance, you start to see that originally, people try to curate these really high quality data sets, right? And people said, like, well, that's the most important thing. But then it's like over years, like as the models have gotten bigger, we've started creating more noisy data sets. So you start getting noise in the data set because you start pulling the human out of the loop a little bit, and you start relying on, self-supervised methods, or, just having the systems effectively just kind of, mining for data, right? And then you end up with a lot of errors in the labels and so forth. Now, just because you have a bit of error does not necessarily mean that it's actually bad. Sometimes having a little bit of error can actually help the model not get stuck in certain things, right? And so you do need large amount of data. And to that point, I would say think about the number of simulations that we would all run, right? Just globally, just think about the number of Gem 5 simulations alone that you and I probably run. Forget even what's happening in the companies, just the Gem 5 simulations that are being run academically and even within my lab right now, probably. Right? What do we do with all that data? We basically get the paper out. I guarantee you the students probably got it in some directory. He or she will forget about it, once the paper gets in, right? And then we just kind of like, at some point just kind of, archive or erase it. We don't really use it. And I think like that's a wasted opportunity, especially for a domain that is quite specialized, right? There's a lot of domain knowledge you need to have to be able to kind of, understand how to work with things. Just, I'll tell you a little bit about a project that we're actually doing centered around data in Architecture 2.0 later on. But one of the very basic questions just yesterday, one of my students, Shwetang, asked the models was, is data movement generally more costly than, compute? Right? Now, you can, by and large, ask any starting a PhD in architecture, and this is probably one of the first things we try to teach them. And guess what Mistral, Claude, and ChatGPT come back with, right? They say, no, data movement is actually not costly. Now, of course, once you start asking them, they'll rationalize this and kind of come up with, all kinds of excuses about like, oh, it really depends on what data you're talking about. Oh, it depends on what compute. Yeah, but if you ask a vanilla student, it kind of comes down to this point about, a very basic question, right? And these models are not able to get it. And so, but a lot of that domain knowledge is kind of inherently captured in a lot of the data that we're inherently throwing away today. I think that's a lost opportunity for us. And so this is where I think a very simple thing for the quantity side of the world would be, what if we could just create a plugin into Gem 5 or many other excellent simulators that are out there, right? Like within GPU Sim, all kinds of different things, even for accelerators, even for time loop and all these, modeling-based systems. What if we could kind of inherently create, a platform agnostic backend where we're able to suck this data into some cloud service provider where, it's open for the architecture community to be able to tap into. That gives us a wealth of data on which we can start training at least open source models in order to do basic tasks like prediction and optimization, right? And just be able to do it really well. So that's purely on the quantity side. It's going to run over to the quality side. Of course, now as you kind of make the data sets noisy and as you start implicitly injecting errors in, then you got to worry about the quality of the data. And I think for regulating the quality of data, one of the key things you'll ultimately need is some human in the loop element, right? And I think as a community, we have to start thinking about training our next generation of PhD students and engineers and so forth to help us kind of get that higher quality so that we can end up with something that's like a reasonable data set with low error, right? And this means labeling the data sets and so forth, right? And I think that gets into what kind of data set. If it's a ginormous Gem 5 simulation log, yeah, that's very, very hard to kind of really sort of streamline, right? Because what are you going to label in that thing? It's very hard to label. The best you can do is have some sort of metadata about the conditions of the experiment and so forth. Right? However, we can still curate high quality data sets about basic information and questions such as like, is data movement more costly than compute? That's a QA. Right? If you kind of go back and you look at NLP models, by and large, they've worked on these kinds of QA data sets that we have, right? Question answering paired data sets, which test the model's ability to understand the domain. So if we can create those kinds of data sets, which I think students would be able to help, and so will the community, then I think we can start sort of bootstrapping this quality oriented data sets and start creating benchmarks, which is in a whole nother area outside of the data itself.
Yeah, I have some follow-up questions here. So I guess what I'm kind of picturing based on what you're saying, because I used as one of the early developers of Gem 5 way back in the day. And one of the things that we had tried to do was, have a very rigorous set of statistics about all of the major structures, and they just get all spit out at the end. And then there would be maybe a little bit of labeling about like what happened in this particular simulation so that you could distinguish, what happened between this run versus that run or what have you. And so I guess in your mind, are you imagining something like this where you essentially spit out a bunch of data saying like, okay, if the ROB size is 8, let's have some ridiculous number, and the L2 cache size is 4 gigabytes, which is also a ridiculous number, then it can essentially glean out some correlative stuff where when you have maybe a more reasonable number for both of those, or isolate like what is cause and what is effect, or what is at least correlated when things are happening. Mm-hmm. Is that what you're talking about? Or do you necessarily need some sort of label to say like, hey, I believe this run is testing new structure A, because all the run to run, some of them may have a new structure that wasn't there before at all, that introduces new relationships, or some of them might have bugs, which we would have tons of bugs where like, oh, these results don't make any sense. Like somebody had to look at it and say like, oh, this doesn't make any sense. Mm-hmm. I guess what I'm imagining here with respect to the generation piece, there is a structured generation of like, what are we spitting out? What are the pieces of data? What are the structures? And then there's the sort of description, or I guess label of it. Like if you invent a new widget, mm-hmm. How does that then get incorporated?
Yeah, I mean, at the end of the day, we're always having these unit tests in some capacity, right? So in the case where we end up with something new, I mean, we will still have to continue doing what we are doing today, right? Which is kind of writing these custom unit tests and making sure that we're actually right about them. But at a macro scale, what I would say is that if you're looking at it from the holistic system, then I would very much do whatever we are already doing in many of the big AI systems, right? So, when you're hitting, let's say if you're hitting something like DALL-E, for instance, right, and you're generating an image, given a prompt, you have to generate an image. Well, the prompt doesn't directly go straight to the model, right? It doesn't go straight into the backend. You've got a whole bunch of infrastructure that's actually sitting in the front end that's actually guarding the prompt and making sure that the prompt is intentionally good and it's well-meaning and so forth, does not mean that the back end is completely, going to be safe, right? Because you can generate pretty harmful images today with just state-of-the-art models, right? So you still have to kind of have some checks and guardrails in place, which is what the front-end classifiers are typically designed to do. So in a very similar way, you would train simple classifiers, I would think, that are able to spot anomalies that are happening inside the system. And so you could effectively use that to kind of have some mechanism of a feedback signal that comes back to the architects who are designing the system. So I'd still go back again with the human in the loop being the most critical element of this all.
In addition to the technical challenges that you discussed, it looks like there is a big part of the community contributions that's required in order to bootstrap this entire ecosystem. You've been involved in multiple both open source and community efforts over the years, including MLPerf as a founding member. So can you talk about the importance of such open source contributions along with industry plus academic collaborations in advancing this particular field, and also how do you think about bootstrapping this particular ecosystem for architecture 2.0?
Yeah, that's great. I'm glad you're asking about that. Yes, it is true that I'm a super big proponent of doing community-driven efforts. And in all honesty, the kudos and the credit really goes to kind of things that I've learned when I was a student, looking back on what the community was doing. I mean, the community built the Gem 5 simulator. The community also helped contribute to GPU Sim, but Torch started. And as a community, every once in a while, we kind of reach a point where we really need to come together to create something that'll unlock the next generation of ideas and research that can come out, right? And so that's where I really draw a lot of the inspiration from, is kind of looking at how we have done these big mega projects that are now sort of the backbone, right? So from that sense, when you talk about architecture 2.0 or kind of building this data set, one of the things at ISCA we're actually going to talk about at one of the workshops is we basically have created a massive corpus of last 50 years of architecture research. And we haven't talked about this, we will be talking about it, but it's coming. And what we have actually done is we've started creating a data pipeline where we have data annotators, basically, undergraduate and graduate students effectively labeling certain types of questions because they need domain expertise, such as the one that I was talking about, which is data movement related thing. And we've started creating that data set. And we originally started with the ISCA 50 retrospectives, where we collected all the retrospectives, which is a very small sample that was put together by Jose Martinez and Lizzie John from last year. And we did a QA data set around that, and we took that data set and we fine-tuned some of the open source models, which are actually performing bad on architecture. And we immediately saw a spike in the ability, so which was a clear signal that even with a little bit of a curated corpus, you can actually improve their domain knowledge about architecture. And now we've effectively expanded that to be the last 50 years worth of architecture research. Architecture, again, I said, is kind of encompassing both traditional architecture as well as EDA kind of flows, so papers in that sort of corpus. And we've created a pipeline which allows us to kind of start labeling as a community. And this is what we're actually hoping to announce pretty soon at one of the ISCA workshops, and then write a subsequent blog to engage the community. And I think this is where, for instance, for people who do believe, okay, AI/ML can be a useful tool in our toolkit, it'll be a wonderful opportunity to contribute to help shape it. In my vision, it's first we start labeling the data sets. We start labeling, then we start fine-tuning models. And I would love for us as a community to have a collection of open source models that are actually domain specific to us, right? And then you can start trying to improve their knowledge across various ways. And this is where benchmarks become critical, right? Because benchmarks in my head are a way to kind of bring the community together, because everybody has to agree on what are the interesting tasks that we actually want to solve first. And then you can start creating a roadmap that allows not only apples to apples comparisons with benchmarks, but benchmarks are also sort of the North Star. For instance, when we wanted to go to the moon, we weren't necessarily talking about, oh, this is the specific navigation system I have in Apollo, or this is the thruster that I have. No, you actually focus on getting to the moon, and then you work backwards and say, okay, what are all the elements that I need to have in order to be able to get to the moon? Then you say, okay, well, I need to have a certain amount of, the thrust capability. I need to have a certain type of navigation capability, right? And you kind of identify all the pieces, and you kind of build a matrix that says, okay, if I can check all these, it tells me that I might be able to get to the moon. And so in my head, That requires a community effort because you have to build that complex matrix for one, right? Which is identifying what are all the tasks that we would need to be able to do incrementally, one by one, so that we can say, okay, someday perhaps we can ask a large language model to say, okay, act like an architect, give me a RISC-V core that's got this sort of, ISA support, and it's able to really optimize these particular workloads. I'm not saying that one LLM is magically going to do it all. I'm saying it might actually invoke other agents or existing traditional non-AI ML tools to actually get the job done, right? So there's the two parts. So one is kind of like getting all the data that needs to actually be put in place, which is kind of what, I think that's a massive community effort. There's no way you can do this just by dumping some data set outside and say, oh, okay, everybody adopt this. I don't think that's going to work, right? We all need to chip in, much like the way, I'm just picking Gem 5 as a poster child here, much like Gem 5 is a community project. We all chip in, right? When my students find a bug, I say, don't complain about it, just go fix it. It's incredible that you actually have a massive simulator that someone wrote for you. Right? So just go fix the bug instead of complaining at it, right? So if we all kind of contribute in that way, I truly believe that we'll be able to kind of build a new set of tools that will help us with hardware design. And I think that's where the community aspect kind of comes in with respect to architecture 2.0.
Yeah, I mean, I think that sounds very interesting. I mean, the way that our community always has worked, it seems, is that there's some sort of thing happening. There's some churn, there's some change, and then there's a lot of discussion, and then eventually there's a congealing around some sort of pillar of how we're going to do things as a community. So we eventually congeal around a benchmark suite, or we eventually congeal around a simulator. There's a few, but there's not, everybody doesn't come and roll their own, right?
Mm-hmm.
Because we sort of realize that collectively it's better if we all collaborate on a few. Mm-hmm. So I think what you're saying, it makes sense. It seems like a tall endeavor too, but that it always is in the early stages. So for some of this, I mean, I'm imagining this big world of possibility, right? Where let's say one of the parameters that's on the table is, say, a new instruction or like a complete ISA change or something like that, right? Because you sort of have to start from somewhere. And as a community a long time ago, we jelloed around a set of instructions, more or less, mm-hmm. right? We might quibble about whether you need fmol or not, or whatever, depending on the situation. But we more or less, they look very similar, barring RISC v CISC. And I guess what I wonder is if we wanted to say explore something different, it seems like what would be necessary is for someone to say come up with a new, say, instruction, and then come up with a new compiler that uses that instruction adequately to come up with the instruction stream that then can be fed into a number of sample machines to be able to produce the data that would be rich enough for an AI to be able to reason about it, mm-hmm. right? Because, if you just say, add one new instruction and then compile one program and put it through one run of Gem 5, mm-hmm. there's no way for an AI to be able to reason about like what it was that might change if you put that in the corpus of everything. Mm-hmm. So it feels, I guess I'm just thinking through how this would work. And it feels like then the kind of work that we do now, which is like, hey, what would happen if we had this new instruction? Then you'd have to do all this work. And you have a sort of a hypothesis in mind, and you set up your experiments to be able to figure it out. Now sort of the hypothesis maybe feels even more vague, or more like, what would would this instruction be a good idea? Then you do all this work and then let the AI say, yes, it would be a good idea under these circumstances for these types of instructions, but you still have to run all the simulations. So I guess I'm just thinking about that process where, as a student, if you have a hypothesis, you sort of have to come up with your experiment set. And now what you're trying to do is come up with an experiment set that is wide and varied enough to produce enough data so that an AI can draw a conclusion. Is that sort of how you picture it?
Yeah, I think like there's an aspect of, yes, we might have to build all the tools and so forth to kind of get to that, evaluating the hypothesis. Now, I think like I'd like to think, as you were kind of mentioning that, I was translating this into a visual in my head where I'm like, okay, if I'm sitting in a room and I'm trying to think, okay, what's the next set of optimizations to perform, right? In my head, I would assume that given all the simulation data that's kind of setting in, for instance, right, from whatever simulators, pick your favorite company and all the tools that are internal, I would assume that I should be able to ask, like, what are the common bottlenecks that I'm actually seeing, and what aspects should I really focus on optimizing, right? And as an architect in my head, the architect of maybe like 2030 or 2040 would be like kind of interacting with an AI agent that's kind of asking probing questions. The AI is really kind of just looking through the minds of data and making connections that you and I normally would not make. And I don't think we don't necessarily have to push it to the point where, okay, just give me the chip, but it's more of an interactive feedback loop, right? That allows the architects to very intelligently brainstorm things, because often architects are kind of doing this today anyway, right? Chief architects kind of sit around and like talking to all the IP modules that are getting integrated in the SOC. And I would think that that feedback loop is very slow today. And I would assume that in the future, the feedback loop is going to be extremely fast, because it's the AI agent is effectively synthesizing all this data and it comes prepped for the meeting, much like any other person. And you can just ask the AI agent like, okay, what would it likely be if I had this sort of configuration, right? Which would be the notion of taking the prediction data, looking at optimizations, right, that it have been performed in the past, and then potentially kind of making some sort of generative sort of an idea of like, okay, this is how I would retweak your design. And so I agree with you, it's inherently nebulous and I don't have all the answers around this, but my hope is not so much that you and I honestly figure it out, but my hope is that we get the next generation to fire up, because they're likely going to think about these things in a very unorthodox manner that you and I probably don't think about, because we're very much stuck in a certain box given the rules and things that we ourselves broke, in order to be who we are.
That's right. They're
Right.
going to be AI native, unlike us.
Yes.
Right. Yeah, that's a fascinating discussion, and also you've painted an exciting vision for the possibilities in the future. So I'm hoping a bunch of our listeners are geared up towards this particular challenge. Um, Switching gears a little bit to another thrust in your research, you've worked on enabling ML in resource-constrained devices, like edge devices, mobile devices, and so on. I think you've christened it Tiny ML. Can you tell us a little bit about the unique challenges in designing both efficient algorithms and hardware for Tiny ML applications, and how would you sort of compare and contrast it against large-scale machine learning deployments? Why is it exciting? What is different about it? What are some unique challenges in that particular space?
Yeah, so TinyML is effectively, really talking about embedded machine learning. And for folks who like, typically when we talk about on-device machine learning, most people traditionally in the industry will say that, okay, that's kind of more talking about mobile devices, right? Our smartphones are effectively the on-device element. TinyML is really not about that. It's really about pushing ML onto, hundreds of kilobytes of memory capacity, right? And so you're really talking about, milliwatt level power consumption, always on ML, specifically in IoT kind of devices or even smartphones. It's always on, some element is constantly listening because it has to in order to detect a keyword. Like when you say, hey, Siri, it's not like the system wakes up, submodule wakes up, right? So certain aspects always have to be on. And the question is, can I fit in neural networks into a few hundred kilobytes or, 1 or 2 megabytes of flash storage that I actually have? And so that's what TinyML really is about. And it's a vastly different ecosystem from the rest of the big ML stuff that's happening. And I would say that it's quite fascinating because it's the perfect melding of hardware, software, and ML. It's that blending of all three that I think is truly what TinyML sort of, is all about. And that kind of opens up the space to many interesting challenges. I mean, this whole ecosystem kind of started about 5 years ago, maybe 5 to 6 years ago, I would say. And back then it was just an idea, and there's a TinyML foundation that got formed around this, where we were all kind of just thinking about what would it be if we could enable speech recognition on a coin cell battery operated device. I mean, that's a pretty damn far shot. That's quite the moonshot if you kind of think about this. This is still 5, 6 years ago, right? And so that's where, and this was also during when I was at my sabbatical at Google, where there was a skunkworks project on, hey, can we actually do this? Can we adapt tools like TensorFlow to be able to run on microcontrollers, much the same way they were adapted from running on big servers and workstations onto mobile devices? Things needed to be stripped down and so forth. And of course, today, if you kind of look at it, there's an entire world of, tiny models all over the place, lots of, optimizations that are specialized for these embedded devices. And this is a space that I think is fascinating both for research and education. I'd say in research, it's especially fascinating because talk about co-design. This is one place people could really use co-design because they're highly bespoke applications. Typically when we talk about co-design, I often kind of, skirt a bit because I'm kind of worried about like co-design looks, complicated on paper. It's lots of innovation, technical innovation, but from a practical standpoint, I'm always like, how is anyone going to take any of this and make sense in a company? I'm not saying that they have to do it today, but even like 7 years from now, where you're asking them to rip apart the algorithms, you're asking them to rip apart the runtime, you're asking them to rip apart the architecture / microarchitecture. I'm like, it's an intellectual exercise that is awesome, but there's an aspect of which just seems completely imbalanced, right? Because often when you're building systems in large scale, you need them to kind of be general purpose to an extent. Right? And when you're talking about TinyML, it's very different because it's highly bespoke. Your Ring doorbell does nothing but pretty much just image classification. It does not have to listen to you. Like there's lots of very simple things that it can do. Right? Your Alexa does not need to see you necessarily. It's mostly just trying to listen to the sounds. Now in the future, I think like I think speech is going to become so common, right? I think this notion of touch. I bet my daughter is going to be like, "What? Why do you use to touch the screens? That's so yucky." Right? That's probably what she's going to say when she's a couple of years older, because she's just going to probably be talking to every single thing. It's going to be like, hey, widget, toast my bread for 2 minutes, bake for 325. All right. It's probably how, and that's a limited vocabulary space where you don't necessarily need big models. You can really get away with highly bespoke models that are highly specialized. And of course, if you can do that, that's pretty incredible. Right? I mean, just think about the world where today you think about AI, you still physically have to interact with it in the real world, right? Like you kind of, you're interacting with some sort of entity. That's pretty clumsy and clunky if you kind of think about it, because you are working around, the machine. In reality, we are having to adapt to what the machine is. If it's truly embedded, you don't notice it. And that's the beauty of like, Mark Wisner's vision about like ubiquitous computing way back, like, at Xerox PARC. They have this idea that you're going to have intelligence spread across everywhere. And I think that's where we're getting to, which is ultra low power consumption, specialized intelligence for specific things that the devices need, and then being able to seamlessly interact with us. Right? And that's essentially why I'm like super excited about the TinyML ecosystem.
Right. I think we have a long way to go to get to that ambient computing where everything just disappears into the background. Like truly magical technology is something that you don't even notice exists, right? You briefly touched upon how TinyML also has a space in education, because for a lot of the other models, especially the largest models, you need like industrial scale machinery to be able to interact and iterate with it at at multiple scales. Can you expand a little bit on how you think this is going to be useful in education? Very broadly, I've thought a lot about how do you teach students about compute architecture, especially in the current times, given that the space is evolving so rapidly. Do you tell our listeners, how do you think about teaching compute architecture? How do you think ecosystems like TinyML or the associated tooling and infrastructure would be helpful and beneficial in teaching students about the different concepts in this particular space?
Yeah, I'm going to talk a little bit more broadly than architecture, because I think architecture's kind of scope is also expanding, especially as we look in this domain of ML. I think an architect who wants to play in the space, for better or worse, needs to understand the ML ecosystem, the ML systems ecosystem, right? So I'm definitely very passionate about education in this space, because I think it like breathes new life into traditional embedded systems that have been taught forever in universities worldwide, right? I still remember the first time I ever was when I was a professor at UT Austin. I went into the classroom, I was about to start teaching embedded systems. And I was like, before leaving my room, my home, I remember I grabbed the garage door opener because I was like, oh, this is a very basic embedded system. It's amazing. It's like everywhere. It's like, I'm going to use this to inspire students. And I still remember, holding it up and I'm like asking the kids, and they were all like, oh, it's a garage door opener. And I was like, this is an amazing piece of technology because it's got all this stuff. And as I was getting excited, I saw their faces going really dull. And I was very perplexed by that as to what was going on. And one of the kids at the front said, I really don't want to do engineering so I can build garage door openers for the rest of my life. I was like, damn, kid's got a point. 2 weeks later, I got my Google Glass and I took that in, and suddenly everybody wanted to kind of work on like embedded systems and stuff. They're like, oh yeah, this is super cool. And I want to do this stuff. I think like for education, I've realized that it's really about kind of, making it relevant with the times with, where we are. And so like, obviously today, when we look at AI systems and so forth, there's a lot of excitement. We build lots of incredible hardware for this, but it's often very inaccessible, right? Think about how often can we actually, go come up with a design that we can actually take, all the way through the life cycle of the chip, right? From concept to doesn't quite happen. But TinyML kind of opens it up to a very exciting space, right? For one, there's a lot of open source ecosystem tools that are kind of coming up. And because the designs are highly bespoke, you can actually do a lot of specialization. And because they're also small designs, you can actually completely, go from your concept to kind of, getting the tape out of this, or whether you're doing it on FPGA, it's so much more practical. And I think the timing is sort of very interesting for education, because you have these open source tools that are just mature enough to be able to pull this off, right? And then you've got an interesting educational area, which is around AI. Everybody wants to do AI, but then often it's like some big model, some big data set that, I can go around asking how many people have actually built a data set. And I can guarantee you often whenever I'm asking this question, probably, one or two people will raise their hands out of 30 or 50 people, right? Very few people touch that. But when it comes to this sort of embedded ecosystem space, the data set is highly bespoke. So you can actually get them to go all the way from understanding how you collect the data, how you pre-process the data, right? Imagine if I have to just kind of wake up a machine that says, when I say, okay, Vijay, that's what I want. Like, well, you can go easily collect all of that data, and you can build a pipeline now and actually train the model, do your optimizations, and particularly deploy it and actually get it to close the loop, right? And these widgets today are literally $5 a pop. I mean, the ones that I have, like, folks can't see this, but like, we actually kind of build these things, right? And they're really, really cheap. And of course, Arduino, Seed, all these folks have started putting out these, MCUs, and these MCUs, these microcontrollers are completely capable of running, these models. So students have an incredible opportunity to deeply understand whichever layer of the stack that they're quite interested in, right? If you kind of look at Songhan's papers, who has also been doing some pretty amazing work in TinyML, for instance, they've been able to build an entire runtime engine that sort of, optimizes it. How often would you ever go out and build a big TensorFlow-like engine to show some incredible capability that you can unlock? You can't do that on a big system. However, in their case, they were able to kind of build a custom runtime model, right? So that kind of opens it up really. And of course, there's lots of hardware solutions, that's like preaching to the choir on like, what it means to build hardware. So I'm not going to dabble into that. But I think that's a really exciting space, right? The one thing though, that's certainly missing in this ecosystem is sort of like there are not enough educational resources around this, right? And this is one of the reasons, like, I think folks kind of know about this, but I started putting together my own class notes, and in fact, Vijay actually knows about this, where I started writing a machine learning systems book that kind of talks about what it means. And originally it was a TinyML specific book, but as I started writing my notes in that, I started realizing it doesn't matter if it's TinyML or big ML. Fundamentals are fundamentals, right? When you do operating systems, yes, there are distributed operating systems and all kinds of crazy stuff when you go to RTOSes and so forth, but you still have to learn 101 operating system. So when it comes to ML systems and architecture, it doesn't matter if you're building a big ML or a small ML. The fundamentals are still the same around all the nuances you need to understand about what happens in an ML pipeline from the point when data comes into the point the data goes out, right? And so I ended up creating this, MLSys book that it's an open source project where people have actually been contributing back. So this goes back to my whole passion about community involvement and so forth. In fact, just this morning, I actually kind of was working on getting the release out because I've been spending an insane amount of time. I feel like until I get the release out, I can't actually rest because there's always something more to do when it comes to these educational things.
So question about the open source notes that you're talking about. That sounds really, really interesting. I'm just wondering, is the model sort of Wikipedia model where everybody can just put their stuff in, or is it a Linux model where you need a pull request and Linus need to say okay?
It's definitely a pull request model. So yeah, so someone has to be, involved in curating it. Of course, there are a couple of people that are, I certainly have been talking to multiple faculty members, and as much as I kind of do the initial drafts, and my students, my research lab is very active. Every time I teach it, my students kind of contribute. Oh, these are interesting seminal references, because the field is moving very fast, right? So the question always is like, how do you sort of keep up with it? And that's the whole reason for making it an open source sort of a project where people can issue pull requests and kind of keep it updated. That said, though, I was still struggling with it, and that's when I kind of reached out to Dave Patterson to ask for a bit of advice on, like, when they wrote the book, they wrote the computer organization book back when things were evolving rapidly back then, right? Like today, we kind of look at it as the Holy Bible, but when they were writing it, there were heated debates going on about what's the right thing to do, what's not the right thing to do, and so forth. And I think the advice that he gave me is kind of what I follow, which is if a company has started putting it into practice, that could be a nice litmus test for whether this concept should be in an educational resource, because it means that there's community wisdom that, yes, this makes sense. The nuances, of course, will be different, but that's sort of like a way of kind of proofing it against the rapid change that's actually happening in the ecosystem. And that's actually worked out quite well.
I think that's a wonderful initiative and also a great resource, not just for students, but also practitioners in this field, because even once you get into industry or you're working in the particular space, because the space is evolving pretty rapidly, it's hard to keep track of all the different developments, number one, but also, as you mentioned, someone curating it and saying these are the essential ideas that you actually need to pay attention to. I think that signal is quite useful, and the process of doing this and curating it is incredibly valuable to the entire field. So I highly encourage the listeners to also go and check out the book. Maybe this is a good time to wind the clocks back a little bit. You're clearly very passionate about teaching. Maybe you can tell our audience, how did you get interested in computer architecture? What is your journey like as you got to Harvard, where you're currently?
Yeah, I'd say that it sounds a bit tacky, but in all honesty, I think I got interested in computer architecture because when I was reading Dave Patterson and Hennessy's book, I remember, I mean, I kid you not, this sounds really weird, but I read it like it was a storybook, or like it was a novel, because it was accessible. I mean, I just kind of picked it up, right? And I was like, who's going to read this massive book? I still remember when they gave it to me, it was like this big fat book. And I'd gone and picked it up at the National University of Singapore because that's where I started my undergrad. Picked it up and it had a CD. I was like, what? Like, who knows all this stuff? And what? I'm going to have to memorize all this stuff. And so anyway, I still remember like kind of just sitting down and like reading through it. And I found it fascinating that it was so accessible to learn something that seemed so complicated that you would normally think that, oh, I have to go to class and necessarily kind of pick it up. And that, to this day, kind of left an impression on me. It's like, oh, it's like when you have a good educational resource where you can learn, you might not be able to master it. Certainly, you need mentors to help you master it. But if you have a good educational resource, then that can really kind of, spur you. And I also think more than just that material, I think it's also the community aspect. I think some folks in our community are very approachable and accessible. And I think like just looking at them as sort of mentors and being like, oh, maybe someday, I can be like them. For me, I honestly feel that that has a bigger impact on you than the actual technical material. And that's honestly how I ended up becoming a professor. I never thought I was going to be a professor, to be all honest. It's just, I was so inspired by my own mentors. Just like, wow, these people are so incredibly smart, yet they're so humble and so nice and so forth. I was like, and they're like so invested in me, even though I don't even know the ABCs of stuff, right? And that, I think, is, for me over time is kind of translated into, we're all technical people, we're all smart people and so forth, but at the end of the day, we're humans first, right? And it's all about relationships, and just being nice and taking care of one another, I think, is far more important than all the nitty-gritty. One of the best pieces of advice that I was given, which I take to heart, from one of my colleagues, Gustavo at UT Austin, back when I was there, was if you can't have a cup of coffee with your colleague and just kind of hang out, forget writing a $20 million proposal or whatever it is, it will never work. If you can't just hang out with a person like the way I'm hanging out with you, Suvinay or Lisa, like, yeah, there's no way you're going to have fun doing whatever it is, right? And so I really feel like as much as we want to invest in technical things and always debate things very technically, I think it's very important to remember that we're all just, trying to learn from one another as researchers, and we're always a learner first in our community. So I think that's kind of really what has kind of inspired me. So I know it's not the classic, I did this, that, and that, and that. I think for me, it's really just incredible mentors and people that I've seen.
That was awesome. I have never heard anybody say that they read Patterson and Hennessy like a novel. Like that is like incredible. I think one of the great things about doing this podcast, and I'm sure you agree, Suvane, is like when we ask this question, like we usually lead with what gets you up, and we usually end with, how did you become a computer architect? And the ways that people became computer architects are very varied. I mean, they run the gamut of different ways, but yours is quite singular. I'm quite amazed. I mean, I enjoyed the book as well, and I remember reading it and thinking like, oh wow, there were several chapters like this is the first chapter textbook I've ever read where I didn't have to like really reread it. Like you read it and it's like gets in there basically line speed. And I was like, wow. And so I had similar feelings, although I don't think I blitzed through it the way you did. It doesn't sound, I didn't consume it like candy.
But it was fascinating though, because I actually, we run a Rising Stars program at ML Commons to recognize outstanding junior students in ML and systems. And Dave, had graciously agreed to kind of, talk to the students. And when I was introducing him, I kind of mentioned this because it left such a positive mark. And I could see, because he said this, he was very happy to hear that, because he said like, oh, a lot of people don't realize how much time and effort, we put into the writing and trying to make sure it's actually accessible, that it's actually really something that people can consume. So, and I think it shows the amount of effort that they must have actually put into just making it available to us, right?
Sure. Yeah, for sure. And I think that also kind of touches on how important it is. Our guests time and time again have talked about how important it is to have good relationships and collaborations and, communication being effective. That's always top of everybody's mind, and how to do as well as our guest list has done, yourself included. And so I hope that maybe this is one of those things where like repetitions will get into our audience's brains. You want to do the technical stuff, but at the same time, you really have to learn how to work with people, be able to communicate effectively, maintain relationships, and that's how you get big things done. Because we are long past the age of being able to do anything on your own that's sort of like of rich value to everybody, right? So
I think it's a new generation. Cliff Young actually recently was visiting Harvard, and he made this really astute observation in a casual conversation where we're saying, when we were building the ML for benchmarks, like, Cliff and Dave were one of the, original pillars in there. And, it worked because we were able to bring all the community together and kind of work collectively, have a lot of grudging consensus in that. And he said maybe it's just the reason perhaps like, nowadays we have to do these bigger community kind of things is because the cohort of people who are actually doing things have been deeply influenced with social media. It's like if you kind of think about the generational changes that we have come through as individuals, right? And if you think about it, like, yeah, that era of people, the current era of people are people who are deeply influenced with social media, which is like, it's a community kind of thing. Everything is kind of shared, everything is discussed, everything is debated, and we do it collectively and we agree to disagree and so forth. And I think that was a very interesting observation that he made. It was like, oh, we live in a different world and people think differently today. So maybe as we move forward, we should work on projects more holistically and more collectively, rather than the way we used to do things in the back. For one, back in the day. For one, systems are much more complicated today, right? All of it, you also need bigger teams. And so I thought that was a very interesting observation that he made about how times have changed and how our culture has kind of evolved. And that possibly is changing the way we actually work together too.
Yeah, I look forward to the day where we can work together only through Instagram DMs. No, I don't. I really don't. But yeah. Well, Vijay, I think this is a really, really interesting conversation. I think we ran a lot of different topics, from Architecture 2.0 to ML Perf and ML Commons and teaching and Tiny ML. I feel very stimulated right now. And so thanks so much for joining us today.
No, thank you so much for having me. Super fun.
Yeah, thank you so much. It was a fascinating conversation. And to our listeners, thank you for being with us on the Computer Architecture Podcast. Till next time, it's goodbye from us.